All right, so as you can see, it's go time. In my little series of explaining some of my macros and how they work, mostly for the people that at my work who have access to them, we're going to talk about Shrinky Dink right here. So this one is super powerful. I use this one a lot. The reason why I want to explain this one, it's going to take a little bit, pop some popcorn. Not only is it just, push the buttons, but I think that what this thing does is accessible, not just the macro. The macro makes it easier to work, but I'm going to explain some stuff where if you don't know about this, you can actually use the equations and stuff on your own with a pencil and paper. But I think it's very important to know these things as a sign person. It affects our industry and affects a lot of industries. I have some examples of that. So let's get into it. So what you're going to do is just grab your go time for those of us. I have this thermometer, which temperature, that's what the Shrinky Dink's for. So those born in the time before internet, before we had iPads and Fortnite, our idea of fun was taking little pieces of plastic and then having your mom stick them in the oven, and then you'd sit and watch them shrink. Yay. Right. And they probably gave us lead poisoning and all that. And I'm sure Kenner or Mattel is going to be coming after me in no time here, or Hasbro. But anyway, bring it, lawyers, bring it. So what the Shrinky Dink does is it uses what's called the coefficient of linear thermal expansion. It is an equation that lets you figure out how much stuff is going to shrink or it's going to grow, expand over a certain temperature range. Super handy, especially for our industry. But most of us in the sign industry, and before I figured out how to use this, we just do a lot of guessing. We drag our knuckles in the dirt before we discover fire and all that. So it was a pretty good example of, necessity is the mother of invention and all that. So we had a particular job go sideways, and it was because we didn't understand, the basic mathematics of this kind of stuff. So anyway, what I'm going to do is show you how to find this information. I'm also going to show you how to use the macro, but in showing you this, I'll show you how you can sort of figure this stuff out on your own, but all the examples of how powerful this is in our industry, stuff that goes wrong and goes right with fabrication and stuff. So as a designer, when you're laying stuff out and I'm going to use different materials, you think I'm going to use these different materials and mix and match them. Well, you better be ready for the fact that some of them want to grow more than the others, or they shrink more than others. And that's where we get into a lot of trouble. So anyway, so first and foremost, I'm going to show you what you're doing with this, like what these equations are for. And I'm just going to use a quick little example here. So let's say you have a molecule. So what we're dealing with, just to keep it simple, it's atomic, whatever, but we're just going to deal with molecules. So let's say this is a molecule of, right here, we'll use the Tufac. So we use Tufac polycarbonate. It's UL friendly, things like that. But you PAL-SUN, any of that stuff. So the idea is you have a happy little molecule here, and this little molecule is at this temperature. So you're going to need the temperature that it's at. So let's just say it's 72 degrees. It's a nice day. And so in order to make a sheet of this, you're going to have multiple molecules click together. So let's go ahead and I'm going to use my line them up here. I'm going to set that to 0. And let's just say we're going to have 10 molecules. So I'm going to make 10 molecules, and I'm going to make them with a spacing of nothing. So here is a sheet of polycarbonate. We have our little molecules all happy at 72 degrees right here, right? So let's say that it's a hot day, and all of a sudden we live out here in the desert. We see temperatures 127 sometimes when it's really, really hot. That's just ambient outside temperature. I have done temp guns of certain vinyls and dark colors that have a surface temperature of 160. We temp gunned for fun one time. This is what we do for fun. We temp gunned our dashboard one time in one of our work trucks, and it was 180. So we see temps. So just for ha-has though, let's just throw an outline on this. And I'm going to make it red just because it's hot. So at 160, this molecule has now expanded this much. Now you take that, we're going to go ahead and group that, and then we're going to go ahead and make another 10 Now you can see if this is 72 degrees, this is 160 degrees, you can see how much all of this is going to grow. And what this equation is doing is giving you the information of how much space is going to be here between each molecule. So that's the whole idea. I'm just kind of showing you this is what you're measuring. Now, you can go the opposite direction and you do an inline. So we'll do the same inline. Let's just say an inline of 0.125. And I'm going to get rid of that, and I'm just going to make it blue for cold. And then I'm going to make another 10 of those, and I'm going to make it go that way. So let's say that the final temperature would be 20 degrees. So you cut this at 72. This is how long it is. The same 10 molecules at 20 degrees is this size. The same 10 molecules at 160 degrees would be this long. So what that coefficient of expansion is telling you is this. It's going to tell you how much you're going to be moving based on your different materials. So getting back to, so that's how this works. Okay. So getting back to the actual macro. So what you need is you need four things. You need a length in inches of some sort. So either the X or the Y, and that's what the linear part. So the coefficient of linear thermal expansion, but let's say I have examples of a Luca bond here. So we'll get into this here, but you can see right here where it says coefficient of linear thermal expansion. The linear part is what we want. You want to make sure, because there are coefficients of thermal expansion that are volume that go in all directions. Think of like a loaf of bread that's baking and it's kind of puffing up. We don't want that. We want linear, where this is just showing you in one direction, one measurement in a line, linear. So as long as you have that, you need four things. You need the length, and then you need the temperature at which you're cutting the piece. So it has to be, whether it's ambient, but basically it's the temperature that that material is. So if you're going to chop up some Tufac polycarbonate, you need to know the measurement of the temperature it is. And then you need the other two are the temperature of the coldest and the temperature that it's going to be at the hottest. So those four measurements, one is the length, one is the cut temperature, and either the coldest or the hottest if you want to figure out if it's going to grow or shrink. So how do you find that information? Well, I already have the usual suspects right here, but in order to go find those, things like aluminum and steel, concrete, those are kind of out there. Those aren't really made by a company. So you can go onto websites and find engineering examples, things like that. That's where I found these. These are pretty constant, pretty standard. They are slightly different for alloys. Like this is a 6061. It makes no difference. I think 13.0 was like 5052, whatever. Steel, same thing. Your different chrome mollies versus A36 are slightly different, but whatever, it's close enough. So this is for A36, which is our tubes and most of your framing stuff. We don't really use chrome moly. We're not making dune buggies or anything. Anyway, but I'll show you where to go find these. So you just go on the web. Let's say like here, I went to Sintra. Sintra is the PVC. You know how we use it. We put little pads on there, and then we might stud mount it onto something like here. Well, it's really important that you know how much this is going to expand. And it's kind of funny because Sintra actually does all the math for you. If you look at their sheet, they're actually giving you an example. So I would maybe, if you're not going to use my macro, I would suggest maybe trying this Sintra. It kind of shows you how this works, which is kind of nice of them. But essentially right here, coefficient of linear thermal expansion, they're giving you the number. Now they broke it out into a normal number, but what you're going to do is just move this over the decimal 1, 2, 3, 4, 5, and you'll have 3.3 times 10 to the minus 5. So going back to here, you can see where I have, that's the exponent 10 to the minus 5. Most of these are minus 5. The bigger the number here, actually the smaller the number and less lively. So you can see where steel is a minus 6, but Tufac's a minus 5. So you can see where Tufac polycarbonate is going to be much more lively. It's going to be moving around a lot more than steel, which makes sense. So if you were going to use this example and we wanted to check out what Sintra is going to do, then using the macro, then all you got to do is come down to other, and I gave a plugin for that. So you just type in 3.3 and then it's minus 5, and that will give us Sintra. So but like I say, I went ahead and went to all the websites, but you can go to like Corian. I've already gone to them back in the day. I'll tell you the story. Corian is the whole reason why I know all about this. But you can see here, it says thermal expansion, and it has an ASTM, how they actually did it. And then it gives you, you can do metric, but look for, at least for my macro, look for the inches in Fahrenheit, because America. I know the rest of the world is using metric, but what you're going to do is, go to Corian's website, look around for tech specs. There's a whole, downloads, look for performance characteristics, things like that. Look around in the documents and you will find, these companies do this. A lot of times it's because UL requires it. So UL will make them sort of put up all of this, information, and it never fails that somewhere in there you'll find the thermal expansion. Same thing, so like a Lucabon was the other one. I don't have a Lucabon, but it's pretty obvious. A Lucabon is very popular. A lot of car dealerships now are doing all their facades with a Lucabon. Everything's a Lucabon, which is essentially Sintra with aluminum stuck to it. And again, I went and dug around on their website. I found their technical data sheet. You can see here. And then I cruise down and I find it, and you're looking for coefficient. Usually I look for the actual equation. It's pretty unique over here. And then there it is. So they use the ASTM, whatever, blah, blah, blah. So you're just going to take that number and you're going to plug it into down here, which was 1.11 to the 5. So, and that would be a Lucabon. So, all right, so let's have some fun. It is kind of fun to see how much stuff will grow and shrink. So this is the first example of how I use it mostly, is I'm going to build a sign cabinet. So let's just say I'm doing a 6-foot sign cabinet and it's 24 inches. Pretty much everything we do is some sort of rectangle, right, with signs, because we have a copy and it's going to be, it's going to be a rectangle. Now, understand that what you're doing is measuring the amount of molecules, how much they grow. So that being said, understand that the more molecules, the more growth. So you're not going to have the same amount of growth on the Y here as you are on the X. So it's good to just sort of concentrate on the long one, because that's going to be your most growth. But keep that in mind. The smaller, basically the less molecules, the smaller the piece, you're going to have much less movement, because you're only going to have, this many. And then, if you only have this many, there's 4 and there's 4. There's not nearly as much as, look at how much movement is for the same 10. Look how much movement there is, So always keep an eye on your longer stuff, rectangles, things like that. The longer this is, the more movement you get. So anyway, so here's a cabinet. It's 6 foot. And I'm going to go ahead and put a retainer. So we're going to let's do an 1.5 inch retainer. And I'm going to go ahead and combine that. And I'm just going to make it, I use my 10% for aluminum. So here's my frame. Now what I want to do is I'm going to put retainers on this thing. I'm going to have 1.5 inch retainers, and I'm going to have a slide in face. This is my bread and butter for this thing. It tells me how much to shrink it a little bit so it doesn't push against the retainers. You don't know that we're out here in the desert. You don't know how much we get where people come and they install their signs. Other companies come into the desert, and then the customer's calling us going, my sign face is either pushing, the retainers are bending, or, polycarbonate face is all wavy. It looks like crud. It's bulging, help me. So this is how you stop that. All right. So like I said earlier, you need those 4 measurements. You're going to need the temperature of the material when you cut it. So an example for us out here in the desert is our router tables they're essentially in glorified sheds. They have swamp coolers, but it can actually get pretty warm where we cut our materials, our, sheets and stuff. So let's just say we'll be generous, and it's, it's mid-March, it's April, whatever. It could be 85 in there. So we'll set the cut temperature at 85. And let's say that it's going to have some dark vinyl and it could get pretty hot. So just to be safe, I'm going to keep it at 160 for a surface temperature. Anyway, so because I'm in open warfare on typing, you're just going to you're going to select the shape and hit X, and it's going to autofill your X for you. So it's 6 foot. And then since we're going to do a tough act slide in face, because we're good with UL, I'm going to hit compute. and it's going to give the overall, it's going to grow total. So close to 1/4 of an inch if we cut it at 85 degrees and it grows. Now, let's just say that that cut temperature, it's more like February. And again, because we're in a glorified shed, sometimes it gets pretty dang cold. So let's just say it's, we'll say it's 60 degrees. And again, this is where it's really important to know this cut temperature versus your final. And then I'm going to go ahead and compute that again. And now we're almost over 1/4 of an inch of growth. So let's see what that looks like. So we're just going to go ahead and hit bam. And that's going to give me my face. And I'm going to make that red. And so if you want to grow that using the macro, all you got to do is select the shape, push your buttons, and it's going to grow it that much. On both sides, it's going to split it. So you'll see now up here in the top left, it's 72 and 0.27. So that's how much our face is going to grow if we don't allow for the shrinkage. And then also it's interesting, let's take the Y dimension, which is 24. It's not going to grow nearly as much because it's only, there's only so many molecules this way as there is this way. So if we hit compute, we have 09, and I'm going to go ahead and grow that. And then I'm going to go ahead and align it to the bottom again because it's going to be in a retainer. So if we have a cabinet that is 6 foot by 2 foot, and at 60 degrees, I route some polycarbonate at its hottest day, this is how much it's going to be wanting to push up against retainers. And this is why you get wrinkles, bubbles, and it looks like crud. So you need to go ahead and allow for that. So this is what I would do. Since I have this information, I'm going to go ahead and create a BAM again. Boom, like that. All that does is just create a rectangle around a shape without typing. And then since I know that the X and the Y, I know that the X is going to be 0.27. I'm going to go ahead and just be safe. And down here on my corner kick, I have a thing that will just chop that off. So I'm going to go ahead and take 1/4 inch off each side. Even though it's 1/4 inch overall, I'm going to shrink this by half. And so if I push this button, it's going to take 1/2 inch. That takes, or no, I don't want that. Never mind. Yeah, I want to take 1/4 inch off each side. There you go, like that. So what I'm going to do there is I'm building in a lot of safety. So there is going to be my sign face. I'm going to make it blue. And then I don't mess around with trying to equal the top with the, the 24 only grows 09. I'm just going to go ahead and take 1/4 off the top as well, just to make it symmetrical. But we know that there's plenty of room there. That's definitely not going to move around. Now, some old school people might say, well, I just take 1/4 off anyway. That's just my quote unquote rule of thumb. But as you saw, your numbers, they can, a bigger piece can really grow. So it's best to know. Why not just know instead of kind of using old school, methods of like the migration patterns of the elk in the north and things like that and the astrological signs? Why not just use the math, and that way for sure you're within spec. So what I'm going to do is I'm going to send this, if I'm going to make this cabinet, I'm going to make the cabinet to these specs here. The cabinet is going to be 24 by 72. I'm going to send that to fab, but I'm going to go ahead and send a 71.5 by 23 3/4. I'll use my sizey here and we'll get our sizes. So, I'm going to send this to fab, but I'm going to send this to route, and I'm going to know that those sizes are good. And I'm going to sleep good at night knowing that there's plenty of room for expansion, and we're good to go. Now, if you want to see how much it's going to shrink a particular size, then not so much for cabinets. I mean, if we saw maybe -20, but we know that this face will never shrink all the way down to, 1.5 inches, and it's going to fall into the cabinet. That's pretty crazy. So, I mean, if you have that issue, then you would just make a bigger retainer. But for us, our main concern here in the desert is growth, expansion, wanting to push itself off of the retainers, whatever. So the example of shrinking, though, that I was going to bring up is what got me onto this was we did some signs that required our buddy here, Corian. Now, our distributor, we went ahead and made a monument sign that was skinned in Corian, a nice midnight black. It looked so sick. And then we also did a wall cabinet. And we got with the distributor and they said, yeah, this is out for outdoor use. It's fine because some Corian isn't. So we went ahead and we skinned these cabinets. We made aluminum cabinets. They were face lit. They looked really nice, or push through lit anyway. And we put them up and they lasted a couple seasons. And then one time we get a call and the owner of the place was like, hey, I've got some serious cracks in the faces of my Corian. And we're thinking, oh, maybe, some stress cracks, whatever. No. So we went out and checked, and these had fractured. Absolutely. I don't have any pictures of it, but I would show you. But they were completely fractured. Like a fault line had gone through the face of both the small cabinet that was on the wall over here towards the left. It had just cracked right here. And the main monument, it just worked its way all the way through, but completely cracked, just snapped. And we were baffled because they had already been out in the desert for 2 years. They'd been on site, no problem. And it was like, what's the deal? We always blame heat for everything. Heat breaks everything around here. Heat. And it wasn't until, and again, I didn't know anything about this coefficient stuff. So what happened was we had skinned it with aluminum. We had skinned aluminum cabinets with this. Well, I went and I looked. Now, another resource is going online. You can go ahead and go to your Farmer's Almanac, which is a great resource because it has all the weather data forever, So I went ahead and researched the city we were in, and I looked during those times, January, February, and we had some ridiculous cold snaps. And it got into almost the 20s. And for us, that's pretty cold. So let's take this here. So if we had had this 72 by 24 cabinet, let's say, and let's go ahead and keep it here. Let's go ahead and use our little cabinet example. Now, we skinned it with Corian, and we'll go ahead and use that as the Corian example. And so let's say we had cut it, and I think we did. If I researched, what I did is I got the file and I researched when we had cut it. And I think that day it was like 85 degrees. And then I went in the Farmer's Almanac and I found that it was like 27 degrees that night. So, and this sign was actually bigger than this, but I'm just using 72 as an example. So I'm going to grab that. And then I'm going to go to Corian here. I'm going to select that. And so what's happening is it's going minus now. So when I hit compute on this particular one, it's only 0.07 is how much it moved. But we had one that was almost 10 feet and we had close to a 1/4 inch of a crack, and it matched actually what had happened. So on the Shrinky Dink here, I'm going to use these yellow ones as for my shrink. So I'm going to shrink that down a little bit. But you can see how much, if I do blue here, I'm going to go ahead and just make it blue. So you can see how much this wants to shrink past its frame. And that's exactly what had happened. We had wrapped an aluminum frame with Corian, but the Corian said, hey, I'm not done shrinking. But the aluminum cabinet said, yes, I'm done shrinking, fine. And it actually just fractured itself because of the cold. It had nowhere else to go. So it stretched itself apart. So we did right by the customer. We went and got the signs. We fixed them. But when we fixed them, at that point, I did the postmortem and I learned about this. And I was like, oh, crud, there it is. Like this right here will show me how much. And so using that info, we overbuilt and we went ahead and put a buffer and we oversized the Corian and we siliconed the crud out of it, let it move around. And any kind of fastening, we gave plentiful holes, nice, plenty of play in there, and we allowed it to breathe and move. And that was many years ago. And at that point, that's when I learned that if you're dealing with your plastics, your thermoplastics, things like that, HDU even, you can see it has a -5. It's pretty lively. It doesn't move as much as your polycarbonates here, but and a Corian is essentially an acrylic, so it's kind of all the same. But if you're using HDU or Sintra, like we found there, your Sintra and all that, Lucabon, it's good to know these things. A couple of other examples that we had where you guys might use this too is sign people. Let's say we have a 120-inch bar, and a lot of times to be inexpensive or something, we would use acrylic, 1/2-inch acrylic, and then we would stud mount this bar. And you might have, copy, you have words up here, and then there's a brushed aluminum bar that would be acrylic. Well, we would have customers call and say, hey, our acrylic bar, I came to work and it's on the ground. And what had happened is that it just popped itself off its studs. Well, let's check it out. If you hit X and at 120 inches, and let's say we cut it, it was 85 degrees, but on the surface temperature, it got to 160, and it's plascolite acrylic, 1/2 inch. If you hit compute, it grew 0.36. So if we do another one of these, and then we add it, and then we recenter it again, you can see how much this bar wanted to move. Now, if you also take a stud hole, actually I'm going to do a straight stud. So this is for a tap 1024 and a clearance hole of 0.22. And let's say we put that in 2 inches from the edge, then, and you go here and you move this 2 inches in from the edge. I know this is fairly simple. It doesn't move exactly linear, but you can see where how much this stud wanted to move. It's almost an entire stud over. So what had happened was the bar grew in the sun and it just sheared its own studs off and it popped right off. So again, knowing this information saves us. Also, let's say we've done this before too, where you want to take this bar, but it's even longer. We've had some customers with logos that are very long. So we take two when we butt them up against each other. Well, you can see this one's red. Now the other one is going to want to move this way. So that's not very good because now you're going to have this guy is going to grow and he's red. So you can see the interference that having two of these up against each other, they need this much room to grow and move. So what I'm saying here is you could actually take this and use it as a way of knowing how big a hole to drill. So if you wanted to, you could take this and this ends up being, I just hit a button here that does it for me. But if you go like this is a 0.58 hole. So if you really want to give this thing room, you would essentially drill a 1/2 inch hole and fill it with silicone and allow this to be sort of like a bushing. And then this would be your 1024 stud. And then theoretically, it would allow this thing to do its movement. That's one thing to think of. Or what we ended up doing is just you end up going ahead and biting the bullet and charging the customer for an aluminum bar. So then what we do is we just make this into a dimensional aluminum bar. Let's check it out. If you click on aluminum here and hit compute, it's only growing. And I say only 198. It still moves quite a bit. Let's go ahead and make another one of those. And we'll make this one aluminum. And we'll make it grow. And we'll make that purple for fun. So you can still see how much aluminum still wants to grow. But if we take that and we'll make it purple and we move it over, you can see where it's only about a 1/2 a stud. Now, again, you can go ahead and make a larger hole. So I'm going to go ahead and just duplicate, flip, recenter this. Let's just do a node. It's easier. Okay. So now if I just go ahead and grab this, it's a much smaller hole. But so if you were to drill, this is a 0.4. So if you were to take like a 3/8 drill bit, now let's just go ahead and do that. I'm going to hit a 3/8 hole and hit blue. So you can see if you take a 3/8 drill bit and go ahead and do your hole in the stucco or block or whatever, and then really silicone the crud out of it, then you can see where you might have enough room for bushing. But the fact that you're using aluminum will also mean that it's strong enough that it's not going to rip itself out. So you have a better way of doing that. So what we found, through trial and error, we discovered fire. Now we have running water and electricity in our shop. Is that, bite the bullet, make stuff out of aluminum rather than acrylic, because sometimes acrylic's cheaper and faster. But when it comes to bars and things like this, anytime you add length, I was thinking too, for ha-has, if we were to take a 480 inch, which would be 40-foot piece of steel, let's say you have a big steel pipe that you're going to go install like on a big sign or something. Let's just see how much that grows. So I'm going to grab the X at 480. I'm going to hit steel and I'm going to compute. And you can see that if you cut this at temperature 85 degrees in your shop, but you go ahead and go to a final temp of 160, it's going to grow a 1/2 inch, your steel tubing. And that's not to say also, I forgot that if you change the dimension or you change the temperature of when this is cut. So let's say you have this same bar at 120 inches, but you cut it when it's really cold. So let's say in your shop it's 60 degrees, and then you go ahead and make that out of acrylic. Look at that. I mean, you have 0.48 of difference in how long this thing is going to grow. So I'm going to go ahead and add that. And just for ha-has, I mean, look at that. Look at how much that's going to be very angry. So knowing the materials sciences, and understanding how this stuff works really helps. I'm going to do one last example of kind of working backwards. Or actually another example here. I'm going to go, like cooking shows. I'm like, I have this over here prepared. A lot of companies, we just dealt with this. They'll do push-throughs in this old method. It's an old way to do it, but it works. So we have a sign frame here, or a sign face that's 93 by 23, fine. We have some 10-inch tall push-throughs. A lot of companies will just route it clean through, put the push-through in, and then they'll take a piece of acrylic and they will just glue using, Weld-On or 7000 Lords, 7000 series, and they'll go ahead and just, glue that backer on there, and that makes a one-piece kind of unit with the letters. That works great, and then they'll silicone this on. That works great because we use studs and all that, but some companies do it this way. Problem is, let's look at how much it grows. So I'm going to grab a X, and let's just say that let's estimate that the company has a 72-degree temperature controlled, but they ship it to us, which is what happened. It was dark colors, very hot inside. I'll tone it down to let's just say 140. And let's say it's Plaskolite, then I'm going to compute that. So this backer wanted to grow this much. What happens is you have these letters that are trapped by the aluminum face that doesn't grow nearly as much. And essentially those letters are in shear their whole life. That glue is trying to hold back the rain. You're welcome. It's in your mind now. It's trying to hold back the rain. And it's fighting. And so we had the problem. The customer called us and the letters were falling off. And at one point the wind blew the whole thing off, but this is how we knew we had to fix it. So when we redid the sign, we shot our studs and we did all that. And we backed it up with polycarb and trapped the letters. That's how we do it. But this is a good example of knowing this information is, it's not just, the glue died or, it's just too hot out there. That's why the letters fell off. Well, no, it's science. It's because the material is moving around. So in summation, I kind of look at the thermoplastics, polycarbonate, acrylic, those all are like spirited ponies. And you can't trap them. You can't tie them down. They're going to break free. They want to move around. So you got to think around it. Aluminum, steel, they still move around, but they're just, they're there. So if you're going to be, sticking stuff to other things, if you're going to be combining, you have to know. That's why I was saying this particular macro, I was wanting to get to it because it's very powerful. But also you don't need my macro to know this. Go find this information, get out your calculator or your slide rule, whatever, and figure it out. And it really, and it's going to mean that you're not going back there, scratching your head like we did with our Corian signs going, what happened? I don't know what happened. Now now there's stuff to look for. One real quick one as well. It doesn't have to be outdoor, but especially for for us in the desert. Let's just say we're doing ADA signs. We're doing signs that are internal to a hospital, or we're doing signs to a hotel. Now, these are fancy little signs that are oftentimes made indoors. They're Graviply or they're being UV printed or something. A lot of times we cut these on the laser. So for us, again, because our routers are in a glorified shed, but we also have some production happening in temperature controlled, air conditioned 72 degrees. This right here is very important to know that let's say we have a 12 by 12. Now, remember what I said, the lesser the molecules, the lesser the shrink, and that's fine. But sometimes details matter. And if you're trying to make a piece of artwork, then, jewelry, very nice stuff. Let's say we route these outside and it's 95 degrees in our shed, but you're going to be bringing them back in and working at 72 degrees. Then when you route this at 12 by 12 and you send it to the router, but then it comes back into what we call our laser shop and our guys start working with it. Let's just see how much, if it's, let's say it's acrylic, that's not much, but it's something, it's there. It's 0.01. So let's go ahead and shrink that. And we're going to go ahead and go blue on that. And then let's say you're attaching it to an aluminum backer. So that same router is going to route the aluminum backer at 12 by 12, and it's going to route it at 95 degrees. And then you're going to bring it in to work with it. But aluminum is going to contract differently than acrylic. So now you're at 0.006. And I'm going to go ahead and shrink that. And so you can see where it's not that big a deal, but you're going to get two different sizes. Your 12 by 12 square that you sent to the router is not going to be the same 12 by 12 that you see. So I'm going to go ahead and just line it up to one side. So you can see where that difference there is going to be close to a business card, you know? So you want to keep an eye out for that kind of stuff as well, is like, where are you cutting stuff? Where are you working with stuff? Another thing is, what if you take this then and you now have this thing at 72 degrees and it's this temperature, right? So you go up here, it's this temperature, but now you go outside and it's in the summertime like we are out here in the desert, and you leave it in the truck. You put it in the cab of the truck and you leave it there for an hour because you're loading the truck, but you're taking it to the hospital because it's going to be cold there. Let's go ahead and say that the truck is 150 degrees. Now this thing is going to grow 0.02. So it's going to get very grumpy. So whatever you've like, you know, what types of tapes you used or adhesives or anything, it might want to, you know, it's going to change that. So you have to keep in mind temperature controlled. If you cut it at 72 degrees and it's going to end up in a hospital at 72 degrees or a hotel, then try to keep it at that. Don't, you know, the big temperature swings are how things are going to be inaccurate. And sometimes you're really relying on, this is important for sliders. You know, like if you're going to do something that says occupied and then you're going to slide it over and it's going to say not unoccupied. Well, if you route this at 92 degrees and then take it inside or whatever, things can shrink, things aren't going to fit. So it's good to know these things. Anyway, so that's enough of that. Thank you for coming to my TED Talk. But I hope this helps. You know, I'm always here for questions. You know, if you guys want to know how to use this more or whatever. But I hope, you know, I encourage you to do the math, and it'll make for better products, be more profitable. Anyway, if you have any questions, hit me up.
Check the technique. Check the technique.